Our first speaker is Sandra Cerrai from Maryland. She will speak about approximation of quasi-potentials and exit problems for multidimensional reaction diffusion equations with noise. Please, Sandra.
Okay, so thank you for the invitation. And okay, so in this talk I will present some results which I have obtained in collaboration with Mark Friedlin. This is, how to say, the starting point of, a possible future research in which we are interested in studying, if you have a stochastic differential equation in dimension bigger than 1, a stochastic one, then you have to color the noise, and we are interested to see what happens when the covariance of the noise goes to the identity operator. So what happens in this framework. And so we started to study this sort of problems, and we decided to approach the problem of the study of quasi-potential. I think it's red. It's red. I don't know.
That should work.
Probably closer. Yeah. So you see this. Can you hear me? Let's do like this. Now? You can hear me. Yeah, okay, very good. Yeah. Oh. But I think, okay, let's try to do like this. I will speak louder. Okay, so we started to study this problem starting from the analysis of quasi-potential, okay? So I start from this finite dimensional situation just to explain for all of you who is not aware of this sort of problems, but you consider dynamical system in a finite dimensional setting of this type, and F is a Lipschitz vector, W is a Wiener process, and epsilon is a small parameter. And one is interested in the behavior of this system as the parameter epsilon goes to 0. So if O is an asymptotically stable equilibrium for this XX naught, which is the deterministic part of the system, so this X prime equal F, and if D is a bounded domain which is attracted to this asymptotically stable equilibrium, what you have is that the exit of the solution of the stochastic equation from D occurs just because of a large deviation principle, okay? So the presence of this noise allows the process to go out of the domain D due to this principle. So one study the large deviation principle, and so one, in order to study the large deviation principle for this class of system, one introduced the action functional corresponding to the large deviation principle, and the action function in this very simple situation is defined in this way. So it's defined by this integral if phi is absolutely continuous, is a plus infinity if phi is not absolutely continuous. So this is the expression of the action function in the simplest situation which you can imagine. And once you have introduced the action functional for the large deviation principle, one introduced the quasi-potential corresponding to the field F and corresponding also to the equilibrium point O. And you know that, the quasi-potential is defined as the infimum of the values of the action functional over all trajectory which starts from the equilibrium point and arrive to the point X, and you take the infimum over all possible trajectory and for all possible times. And this defines the so-called quasi-potential. And for example, the quasi-potential is an important object in the analysis of large deviation principle, because we will see. So this is the general definition. This is the general definition. It's not working. Okay. So this is the general definition of quasi-potential. But as you see, this definition is implicit. You have nothing explicit. This is just defined as an infimum. And what one would like to F is a more explicit expression for the quasi-potential, because you are really working with quasi-potential, and so it's important to have a better knowledge of this object. And so there is a nice situation in which you can describe the quasi-potential in a more clear way. So when the field F, which appear in the deterministic, the field in the equation is potential, so F can be written in this form, then under suitable assumption on this function u, it's possible to prove that the quasi-potential is just is equal to this function u up to a constant. Okay, so you have an explicit expression, you have an explicit formula for the quasi-potential, and this is a very good thing. As I was telling you, the analysis of the quasi-potential is a very important fact, because, for example, if you want to study the exit time, the mean of the exit time of the process from the domain D, so you introduce the exit time tau x epsilon in this way, then it's possible to prove that the expected time of the expected exit time, the expectation of the exit time, behave like exponential of 1 over epsilon, the infimum of the quasi-potential over the boundary of the domain. And so you see that in this situation, if you have a good knowledge of V, if you can see how V it is, so you can have a better knowledge of this, of the mean of the exit time of the process from the domain. So this is an example in which you see how it's important to have a good knowledge of the quasi-potential. And also it's possible to prove that if the infimum is attained just at only one point, x naught, then the process is going out of the domain exactly at that point. Okay? So this is what is well known in finite dimension, and many of these things which are known in finite dimension are also known in infinite dimension, and we are dealing with the infinite dimensional situation. And so we start from the good situation. So we start from the infinite, we start from a system with an infinite number of degrees of freedom, but we consider a situation in which you have the space variable which is one-dimensional, okay? So in one dimension, we can consider this reaction diffusion equation perturbed by this noise. And here the noise is white both in time and in space. And you know that if you are in dimension d equal 1, this equation is perfectly well defined, you have a solution, and okay, and so you have the process. Here I'm assuming that lambda is strictly positive, b is Lipschitz, so I am in a very good condition. So here everything, the assumption which I am assuming are very, very simple, and b is at 0 is equal 0, and the Lipschitz constant of b is strictly less than lambda. So this means that the deterministic system is collapsing to 0, okay? And I am adding this noise, and I want to see what happens for this for the process associated to this equation.
Do you have Neumann boundary condition?
Okay. Here the condition are Dirichlet or conormal. You can take both conormal or Dirichlet. Okay. So I didn't specify, but if you can think about Dirichlet, but I am in a very classical situation. So as known. The solution x bar equals 0 is an asymptotically stable equilibrium for the non-perturbed semi-flow. And so if D is a domain in the functional space, because here I'm working with domains no more in RD but in the functional space, so if this domain is attracted with its boundary to this, so one can consider the exit problem from this domain, the exit problem for the solution of the stochastic equation. And in the one-dimensional situation, everything is absolutely clear, because what you have is here. As in finite dimension, you introduce the action functional, okay? So in this case, the action functional is defined by this double integral with respect to time, which is fixed, and with respect to the space variable of this expression. You take the square and you get this object. And this is the action functional corresponding to the large deviation principle for that system. Okay, and this is defined in the appropriate Sopole space, otherwise you take this equal to plus infinity, okay? So also in this case, exactly as in the finite dimensional situation, you can introduce the quasi-potential. So you take all values of the action functional over all trajectory which goes from 0 to x, and you take the infimum of all these values for all possible times. And this is the definition of the quasi-potential. So in general, you define the quasi-potential in this way. And again, you see that this expression, you can deal with this expression, you can work with that, but it's an implicit expression. And so you would like to have something more clear. And in this situation, things are much more clear. So you cannot just stop at the definition of the quasi-potential as this infimum, but actually you have an explicit expression for the quasi-potential, because this is a gradient system, and so it's possible to prove that the quasi-potential is given by this expression here. This is the antiderivative. I mean, you have this expression, okay? This is a classical result, which is true, but this is true only in dimension 1, because only in dimension 1 you have a gradient system, because you can deal with white noise in space and time, and so only in dimension 1 you have this explicit expression for the quasi-potential. So, you see, in particular, in this case, you can see the quasi-potential as this derivative, okay? So it has a clear interpretation from a variational point of view. But now we want to go to the multidimensional case. And in the multidimensional case, you cannot use any more these arguments, because the situation is this. You have exactly the same equation. Here you can deal also with more general second order operator, uniformly elliptic, but just to fix, you can just take the Laplacian, but you can take any, more general operator. So you have exactly the same situation here. And you have again this perturbation, and you impose boundary conditions, and in general, you don't have solution for this equation, because you know that in dimension bigger than 1, you have to color the noise in order to have solution in a space of functions, and also you are dealing with this nonlinearity, so you have to color the noise, otherwise you cannot define the process, okay? So, instead of taking white noise in space and time, you have to take, you have to assume some smoothness in the space variable, and so in this way you get existence, uniqueness, and everything. And you can compute the action functional. So the problem here is this, that if you go back to the definition of the action functional here, you see that here you have this expression which is a local, this is a local functional, no problem, because you have identity, the covariance is just the identity. But if you want to rewrite this in dimension bigger than 1, then you don't have anymore a local operator, because in front here you have to take the inverse of the covariance, and you have to take the nominal too. So you don't have anymore a local operator. So it's already, also the action functional is something which is more delicate to treat. It's not anymore something which is classical in the calculus of variation. So first problem, the action functional is not local, and also the quasi-potential is more complicated, and also it's possible to prove that the quasi-potential is finite only if you take x in a smaller Sobolev space, so only for functions which are more regular. And so the problem is this, that now you have this action functional which is not anymore a local operator but is no local, and you get the quasi-potential as the infimum of all values of the action function. So you get something which is even more complex and even more abstract. You cannot say exactly how it is done. And so if you are dealing with problems with the exit, the analysis of the exit points, of the exit times, and all these things, one would like to have something more endable, something easier to treat, and in this case this object is a bit obscure and is not so clear how to deal with this object. And so our idea, we thought, but this was just, as I was telling you, this is a starting point. We were trying to see what happens if you take, if you color the noise with a covariance which in some way goes to identity. So we introduce a regularized noise which depends on some parameter delta, and we assume in some way that this regularized noise converges to the white noise in space and time. And we want to see what happens for the corresponding action functional, and especially for the corresponding quasi-potential. This was our interest. So one can expect, and this was what we are expecting, and this is what we could prove, is that if you take this regularization which goes to identity, so goes to the white noise in space and time, then also the corresponding quasi-potential, which you define as an infimum, corresponds to this object V, which is, the quasi-potential in the case of white noise in space and time, which has this explicit expression. And this does not correspond anymore to the quasi-potential in dimension bigger than 1. But this is something which is perfectly defined in any space dimension. Okay, if you go back to this to the quasi-potential, you see you have this expression for the quasi-potential, but this is something which is absolutely well defined in any space dimension. And so what we wanted to see was if we take a regularized noise, we have the true quasi-potential. Is it possible to prove that the true quasi-potential converges to this object? If this is true, then we have a good approximation by means of something which is more handleable of the quasi-potential. This was our aim. And so we try to prove it. And this is in spite of the fact that we don't have a process in dimension bigger than 1 corresponding to the identity covariance. And if we are able to prove this, then we are able to characterize the asymptotics of the exit times of the of the process in dimension bigger than 1 from a bounded domain, where you have this behavior. When you have these double indices. Okay. So now, just to fix the idea, so we are dealing, and here we are considering this more general situation, so we are considering this reaction diffusion equation, which is perturbed by this noise, which is of multiplicative type, okay? At the end, the conclusion, the concrete expression of the quasi-potential is when G is equal 1, but still we can prove the convergence of the quasi-potential also in the case of a general noise with multiplicative term. So we are dealing with this equation in a bounded domain of Rd, and here D is bigger or equal than 1, and here you have a small parameter epsilon. The boundary conditions are the usual one, the Dirichlet or conormal, and H from now on will be the space of square integrable functions. So here the Gaussian noise is white in time and colored in space in the case of the dimension bigger than 1, and we take the classical expansion of the noise as this infinite sum, and you see here in front of the eigenfunction we have this operator Q delta. And what we assume is that when the dimension D is bigger or equal than 2, you assume that this Q delta behaves like minus A is the realization of delta minus lambda and O with the boundary condition N, and so Q delta behaves like this operator, and here you have this condition on beta, which of course depends on the dimension. And this is assumed in order to have solution, so this is the classical assumption. And what we assume for the covariance operator is that it is but I will enter into more details on the assumption on the covariance operator, but just to fix the ideas, what we assume is that this operator Q delta converges strongly to the identity operator, and it converges strongly in a monotone way.
The corresponding linear process taking values in L squared?
Yeah.
So for each delta, it takes values in L squared.
Yeah. So, and for the coefficients f and g, we assume a smoothness, bounded of derivatives, and some compatibility condition on the boundary. So we assume, we were free to assume reasonable assumption. And also you assume that the deterministic system is all collapsing to 0, just to start, okay? So, under our assumption, these are very classical assumptions. For any epsilon and for any delta, you have a solution which belongs to the right space where you can work, and so everything is okay with the process. So we have a process which is a good process, and so on. So now we can introduce the large deviation action functional, and we introduce the action functional in the classical way. So we define this S, which now depends on delta because it depends on the covariance which I put in front of the noise, and you see it's defined in this way. And this is a no-local operator because you have this Q delta minus 1 applied to this, but I mean, you can take the pseudo inverse and everything. I mean, When this is well defined, this is the expression for the action functional. When this is not defined, you just take plus infinity, and this defines the action functional. And this is something which is well known in the literature on large deviation for infinite dimensional.
G is a real valued function?
Yes.
Your diffusion coefficient is real valued?
Yeah, this one.
Shouldn't you have minus 1/2
No?
Q delta?
No, because the Q is in front of the noise. So it's not Q square. No, it's not. So this is the action functional, and it's defined like that. And so you can introduce the quasi-potential. The quasi-potential is defined in the classical way. And you see that the quasi-potential depends on this parameter delta, okay? When D, as I was telling you, when D is equal 1 and G equal 1 and you have the identity operator, this is the expression for the quasi-potential. And you see that this is an object which is well defined, okay? And I want to get the limit of the quasi-potential, the real quasi-potential, V delta, to this object, okay? So this is the main theorem. The main theorem says that if you take the limit of V delta x as delta goes to 0, this limit is equal to V, and this is true for x which belongs to this space. And this is the space of the regularity of the skeleton equation associated to my stochastic reaction diffusion equation, okay? So this is the right space, and I will show you that this is the right space because I will show you what you can get in the linear case. In the linear case, everything is explicit, and you get exactly this regularity for x. And so for x in this Sobolev space, you get that the limit of V delta is equal x. So, as I was telling you, in the linear case, you can compute everything. You can find this in a paper by I found these things in a paper by Prato, Pritchard, and Sapchik, where everything is computed explicitly. So, in the linear case, if you assume that this operator is bounded and linear and nuclear in H, the quasi-potential is given by this expression. So, in this case, you can write explicitly the quasi-potential. And so if you assume that A and Q are diagonal with these eigenvalues, so you can write explicitly this R, which is given in this form. And so the quasi-potential is given by this. So in particular, if you take Q as minus A to the power minus beta, what you have is that V of x is given by this. And so you see immediately that this is finite only if x belongs to the domain of minus A to the power 1/2 plus beta. So this is exactly the regularity which you need to have, okay? And so you have everything explicit. And so in this case, it means that V, in the gradient case, is this object. In the regularized case, in the multidimensional case, V delta is this object. And if you assume that this lambda delta k goes to 1, what you have is that V delta x converges to V of x when x is in this domain. So in the linear case, everything is clear. But in the nonlinear case, when you don't have this explicit expression, you have to find something more, another way to prove. But just to tell you that the result is the same as the one which you get in the linear case, in the simpler one. So, what about the method? I think that the key result which is required in order to, which is required to prove this convergence is a paper which I wrote, some years ago with Michael Ruckner, and in that paper we proved something which was a bit tough from at least technical point of view. It was quite involved because we were able to prove that the quasi-potential, okay, the true quasi-potential, is the minimum of the action functional. But instead of considering the action functional in the interval from 0 to t, you take the action functional from minus infinity to 0. So you reverse the time. You consider trajectories which are defined for negative time, and so you can introduce in the same way as before the action functional. And if you take the minimum of this action functional over all paths, as I was telling you, defined for negative time, which goes from 0 to x. So this minimum coincides with the quasi-potential. And as I was telling you, this is the proof of this result is quite involved, because here we are in a degenerate situation, because the noise is colored. And so we have to put in front of the noise a degenerate operator. And this means that all proofs about controllability of the skeleton equation, regularity, which are the necessary tools which are required in order to prove this result, become a bit complicated. But still, like in the non-degenerate case, it's possible to prove that V delta is, it's possible to characterize the quasi-potential as the minimum of the action functional, but for trajectory defined in negative time, okay? So you see what is important here is the following. If you go back to the definition, because if you remember, the definition of V delta was the infimum of S0t delta of u over t positive and over all trajectories in 0t, which goes from 0 to x. Okay, so you see that in the definition here you are taking the infimum with respect to all trajectories, but also with respect to time. And with this characterization, V delta is the minimum, but now you don't have any more time, okay? And the minimum is taken in a space which only depends on x, on the point x, which is the point for which I'm computing the quasi-potential. And this makes things, much better. So V delta is the minimum of this functional, which does not depend anymore on time, okay, on this space which depends on x, on the final point attained by your trajectory. It is possible to prove, and this is less complicated, but one still has to work a little bit with that, but it's possible to prove that also Vx can be seen as the minimum of s minus infinity 0 u for u in x, and here you don't have any more delta because you can deal with identity, and so this is the same functional as this one when you replace q delta with the identity operator. And so you see, from this fact and this fact, if you want to prove that V delta x converges to V of x, since this is a minimum on the space xx and this is a minimum on the space x of x, it's reasonable to use an argument of gamma convergence for the action functionals. So if you are able to prove that the action functional S delta minus infinity 0 is gamma convergent to the operator S minus infinity 0, as delta goes to 0, then as a byproduct you get immediately that V delta x V delta converges pointwise, at least for for x which are sufficiently regular, so for x in the right Sobolev space, to V of x. Okay? So here the argument is to use a gamma convergence method. Okay? So what we want to prove is that if you take the limit as delta goes to 0, the gamma limit of this object is exactly this in this space, x of x. For fixed x in this domain, in the domain of minus a to the power beta plus 1/2, you have this gamma convergence. And so, since this family is equicoercive, it's possible to prove that this is equicoercive. By the general theory of gamma convergence, you have that the minimum of this on this space converges to the minimum of this in this space. Okay, so now everything reduced to the proof of this gamma convergence.
Could you recall the definition?
Yeah, I recall everything. Now that this was just a sketch of what I'm saying, just to give you an idea of what I'm talking about, and then I will enter more into details of these things. Of course, if you want to prove the gamma convergence of this to this, you have to go through the study of the skeleton equation associated to the stochastic reaction diffusion equation and all controllability problems which are related to that. So this is the gamma convergence of this really, is really based on the analysis, on a detailed analysis of the skeleton equation. So this is a completely deterministic result because you have to work with the deterministic equation, the skeleton equation. You have to exploit as much as possible the regularity of solutions of the skeleton equation in appropriate space, and by using this you can get the gamma convergence. As I was saying in the title, the main application, the application which we had in mind for this sort of problem is to the analysis of the mean of the exit time of the process from a domain D, which is a basis of attraction for the solution of the stochastic reaction diffusion equation. And what we proved is that, the expected, the mean of the exit time is asymptotically equivalent to this. And this was had to be proved, this result. And if you are able to, once you have proved this, then in view of the main theorem, and by using again gamma convergence, we proved that the limit of this infima converges to the infimum of V on the boundary. And so I can say that the mean of the exit time tau x epsilon delta can be approximated by this. And the value of this is that here this is concrete. You can have this explicit. This is just an integral of the square of the first derivative minus, this is something explicit. And so if you are dealing with a domain which is explicitly given, for which you can compute the infimum of this explicit operator on this boundary, then here you have a number. You have something which you can compute explicitly and not just something which you know that exists, but you don't know how to deal with that. So this is something which is concrete, and so you have a better knowledge of the asymptotics of the expectation of this exit time. So this is the idea, okay? Okay, I think I already talked about. Okay, so I give you the assumption very shortly just to fix the idea, because up to now I was a bit vague. So you have this operator Q delta, and of course here the assumptions are quite strong. So it would be better to have a weaker assumption on this covariance, on the structure of this covariance, but up to now we are able to deal only with this situation. So here we have this operator Q delta, and we assume that is diagonal with respect to the same basis which diagonalize the operator A. And what we have is that these eigenvalues, lambda delta k, behave like alpha k to the power minus beta, okay? And this was what I was saying, that Q delta is like minus alpha to the power minus beta. And here you have this condition on beta, which depends on the dimension and which is the classical one. So this is not related to the problem which I'm studying. This is just assuming in order to have good solutions. And this is the assumption. What we assume for the eigenvalues, that this lambda delta for each fixed k, they converge to 1 increasing, okay? So they converge in this monotonic way. And this is, a technical assumption, but we need to assume this assumption in order to get gamma convergence. But still, there is no reason to assume this. I think that this is related to the argument which we are using, but okay, but this is, so typical example which you can think is this one. So you have lambda delta, which are defined in this way. They converge to 1, and they converge increasing to 1, and this is, the simplest example. And just to tell you, if you have alpha k which behave like this, and beta is behave like this, then this is the classical summability condition which you have for the eigenvalues of the covariance operator. And in particular, here you don't have Hilbert-Schmidt, you don't have anything. You can assume a weaker condition, on the covariance. And also what is important is that the kernel of Q delta is 0. So you can introduce the pseudo inverse and everything. And also the image of all these operator Q delta, they all coincide with the domain of minus a to the power beta. Okay, so they have all the same image. And so the domain of the inverse of all Q delta are all the same. Okay, and they all coincide with this domain. And also what you have is that with this assumption, Q delta x converges to x as delta goes to 0, and also the inverse. For any x which belongs to the image of Q1, you just take delta between 0 and 1. The image is all the same, so you can fix just one image for all, and you have this. And these are the things which which we will use for Q delta. And concerning the coefficients, you see, we assume just for simplicity that they are C infinity because we are dealing with the, we need to use some derivatives of the coefficients. So it's not necessary to take C infinities, Ck up to some k, but I don't want to enter into detail on which k. So take C infinity, and the diffusion coefficient in front of the noise is uniformly bounded. B at 0 is equal to 0 in order to have this convergence to 0. And I have also this technical assumption, which was also in the paper with Michael when we prove this characterization of the quasi-potential as the minimum, the fact that this object does not depend on psi. Okay? And I have this condition, which is again assumed in order to have convergence to 0 of the deterministic part. And I have no degeneracy, and again, because I needed to divide by g, so I have to assume that g is far from 0, okay? And this was not assumed in the paper with Michael. In the paper with Michael, we were not assuming this, but that was... And also I assume, and here I didn't give this assumption because it was too long, but I have to assume some compatibility condition of these coefficients with the boundary condition. So for example, if we are in the case of Dirichlet boundary condition, you have just to assume that B and G and their derivatives up to some order vanish at 0, okay? So you need this compatibility condition. And they were also assumed in the paper with Michael. So once you have this, I go to your question and I introduce some basic facts about relaxation and gamma convergence just to fix notation and do, these are well-known facts, but if you have n of x denote the set of all open neighborhoods of any point x in this metric space capital X, and so f is lower semi-continuous as well known if this set is closed, is coercive if the closure of this is compact, and also a sequence is equicoercive. A possible definition of equicoerciveness is if you can find a lower semi-continuous coercive function psi such that all these fn x are greater or equal than psi of x for any x in this metric space X and for any n. So lower semi-continuous, coercive, and equicoercive. These are the sort of function one has to deal with when is working with gamma convergence. And so I need also the definition of a lower semi-continuous envelope for a function. So if you have a function f which maps this metric space X into R bar, you can define the lower semi-continuous envelope as the supremum of g of x for all g which belongs to this space, and this is the set of all lower semi-continuous functions which are less or equal than f. Okay, so you start from f, you introduce this set of lower semi-continuous functions which are less or equal than this f. You take the supremum of g of x for all g in this set, and you get the lower semi-continuous envelope. And of course, you can say what is the relation between the lower semi-continuous envelope of f with f. So first of all, and this is important, the lower semi-continuous envelope, lower semi-continuous is a lower semi-continuous function, okay? Even if f is not, this is and also this function is less or equal than f and is bigger or equal than any g in this space of functions. So you can see that the lower semi-continuous envelope of this f is the greatest lower semi-continuous function which is majorized by f, okay? So, since we are dealing with this lower semi-continuous envelope, we need a characterization. So we need to know when a function is the lower semi-continuous envelope of some other function. So we need a characterization. And there are several possible characterizations. This is a huge subject. But the characterization which we use is this one. So if you have a function f, its lower semi-continuous function envelope, here is envelope, is characterized by these two properties. So if I fix any x in the metric space and any sequence which converge to x in this space, then the lower semi-continuous envelope at x is less or equal than the lim of f of xn. And on the contrary, if you fix any x, there exists a sequence which converges to x in the space x, such that the lower semi-continuous envelope at x is bigger or equal than the lim sup. So if you want to prove that some function coincide with the lower semi-continuous envelope of some function f, you have just to prove these two conditions, okay? And these assure you to have to know what is the lower semi-continuous envelope. And now I go to the definition of gamma convergence. The definition of gamma convergence is this one. This is one possible definition. You introduce the gamma lim inf and the gamma lim sup, and then you say that you have the gamma limit if they coincide. And so you define the gamma lim inf of a sequence of functionals in this way. You take this functional, you take any neighborhood of the point x, and you take the infimum of fn for n fix over this neighborhood. So you get something which is less or equal than fn of x. Then you take the lim inf with respect to n, and then you take the supremum with respect to all possible neighborhoods of this point x. And in the same way, the lim sup is defined in the same way, but here instead of having the lim sup, you get the lim inf. Okay? In general, the notion of pointwise convergence and gamma convergence, they don't have anything to see the one with the other. So you can have a situation in which you have gamma convergence and not pointwise convergence. Case in which you have pointwise convergence but not gamma convergence. Cases in which you have both convergences but they converge to different things. So they are really two notions which are, under further assumptions, you can have that uniform convergence of or pointwise convergence imply gamma convergence, but you need extra assumption, okay? But in general, if you just have gamma convergence and pointwise convergence, these two things are no relations. And so one says that this sequence of functional is gamma convergent to f if the lim inf and the lim sup coincide, and this is the gamma limit, okay? I'm not able to explain too much of this gamma convergence because I learned what I need, but there is so much to learn about these things. And so this is one possible way. This is the theorem which we use in order to prove gamma convergence, but of course there are several characterizations. But one possible way is this one. If you have a sequence which is decreasing and converging to f pointwise, what you have is that this sequence is gamma convergent not to f, but is gamma convergence to the lower semi-continuous envelope of f, okay? So this is why I had to pass through the lower semi-continuous envelope, because I had this sequence of functionals, they were decreasing, and this is why I introduced this condition on the eigenvalues, because I wanted to have something which was decreasing. It's decreasing to the action functional corresponding to delta equals 0, but then I have gamma convergence only to the lower semi-continuous envelope of the functional S. So the next step is to characterize, to see what is this object. So, and the theorem which allows to go from gamma convergence to the convergence which is written here is the following one. If you have a sequence which is equicoercive in x and gamma converges to a function f, then this f is coercive and the minimum of f is the limit of the infima of fn. Okay? And so in this way I get this result. So let's try try to prove gamma convergence for our functional. And as I was telling you, the basic space, the space where we prove gamma convergence is this way, is this space. And this is the space which I got by proving that the action function is actually the minimum of the quasi-potential is the minimum of the action functionals for negative time, okay, from minus infinity to 0. So this is the basic space. This is a Banach space with a sup norm, so everything is okay. And now, unfortunately, I have to introduce some, auxiliary spaces as usual. So I define this h of u, which is this difference divided by g, which is the expression which appears in the action functional. And yx is the space of u, which belongs to this space. So our trajectory defined for negative time, which goes from 0 to x, and also belong to this Sobolev space, which is the space of functions which are once differentiable with respect to time and twice differentiable with respect to x, to the space variable, and which satisfy the boundary condition. And also this condition is satisfied. So if you take this expression and you compute q minus 1 of this expression, this has the norm of this object in L2 with respect to time and space has to be finite. So this is the reference space, and this is an auxiliary space which is required in the proof. So once you have this, I introduce these three operators. This one and this one are the operators which I'm dealing with, and this is an auxiliary operator which I need to prove my results. So S delta is 1/2 Q delta minus 1 of H of U. I have already written before this for U in Yx, and it's plus infinity for U in Xx minus Ux. And this is almost the same. You see what is the difference? The difference is that here, so these and these are almost the same, but the difference is that here I define this as this. You see, they are defining this in the same way, this way and this way. But here I'm taking U in Yx, okay? So I am assuming the condition that, I am assuming for S tilde that Q1 minus 1 of H of U in L2 minus infinity 0, L2, this is finite, okay? In this case. And in this case, this is just the functional, which is defined in this space and intersection with the Sobolev space where everything is well defined. Okay, so in general, this S tilde is bigger than this S. They coincide here, but outside of here, this becomes plus infinity, and this can be finite, okay? And so what you have is that S tilde is bigger or equal than S, and they coincide on the whole space of x of x, and they coincide in this smaller space, which is, as I was telling you, which I introduced just for the proof, okay? And so what it's possible to prove is that the functional S is coercive and lower semi-continuous. And the proof of this result goes exactly as in the paper of Sowers and in the paper with Michael. The only thing which has to be proved in this particular case is that if S of U is less or equal than R, then you have this, regularity and this bound for the for UT. Okay? But once you have this, then you can apply exactly the same arguments which one has in the other paper. So, but this is important because this allows to prove that S is coercive and lower semi-continuous. So, we have immediately that the gamma limit of S delta coincide with the lower semi-continuous envelope of S tilde. Okay? And in fact, you have pointwise convergence, and also you have this monotonicity, and so you have that this S tilde is gamma convergent to the lower semi-continuous envelope of S tilde. But of course, here we have to see that the lower semi-continuous envelope of this S tilde coincide with S. And this is what is written here. if you take X in this space, then this coincides with this. And in particular, you have gamma convergence. Okay? And as I was telling you before, due to the characterization which we have for the lower semi-continuous envelope of S tilde, we have to prove that for any u and un such that this holds, then this is satisfied, and this is immediate, this is trivial. And the difficult part, which takes, a bit to be proved, is that if you take u in xx, there exists a sequence here such that S of u is bigger or equal than this lim sup. Okay? And this is the more complicated part, because we had to construct explicitly this sequence, and for this sequence we had to prove that this sequence was convergent to U, that S of this sequence was convergent to S of U, and that S of this sequence was actually S tilde of the sequence. But once you have proved this, then you have this, and then the proof is finished. So now we go back to our problem. This is the action functional. It's possible to prove that V of x is this minimum of S of u on this space, as I was telling you. S delta is this one, with this Q delta minus 1 here. And so you see, also in this case, it's possible to prove that V delta is this minimum, is the minimum of S delta over this space. And in particular, what you get is that this V delta is finite only if X is in this smaller space. This you can see from the analysis of the skeleton equation. And so you have this result, and this result is proved just by using gamma convergence, because you have gamma convergence of S delta to S. This family is equicoercive because you have that S delta is bigger or equal than S. S is a coercive operator, lower semi-continuous, and so what you have is that, you have the convergence of V delta to V. This finished the result. I have something also about the exit problem, but I think that probably, I don't know, you are too tired to speak about exit problem. But there is the second part which deals with the exit problem, and in which we apply these results. So I stop here.
So we have time for questions. What you call action functional is the same as rate function, yes? So, yes?
It seems to me that in the classical approach to exit problems for a finite dimensional case, one proves large deviation principle uniformly when the initial condition belongs to some neighborhood. Did you try to do it this way? Was it more efficient? It seems to me that gamma convergence somehow more or less is the same thing. Maybe I'm mistaken, because I'm not familiar with gamma convergence at all. Did you try to?
No, I didn't try. Our starting point was this. We look at, we have this expression for the quasi-potential in the one-dimensional case. You see that this object is well defined in any dimension. And so we thought, why not to prove that, the quasi-potential, which is given in this complicated way in dimension bigger than 1, converges to this. And since we had that both the quasi-potential and this operator and this functional V were obtained as minima of some functional in the same space, then really for us it came natural to introduce gamma convergence, because I didn't know at all anything was about gamma convergence. We had to work with gamma convergence, but we knew that if you have gamma convergence, then you have a convergence of the minima. And so this was the reason why we took this approach, and we decided to use gamma convergence, because it seemed to be natural. But I cannot say that we tried to use other ways, and no, I cannot say.
But I think there was something in the book by Freding Wenzel that you need to consider not only at point 0, but in a neighborhood,
That's right, yes.
and to prove uniform convergence. But you didn't.
No.
Okay, some comments? Okay, so thank you again, and